started, guys. Welcome again to part 3 of our simulation productivity series. And in the last two sessions, we've talked about other ways to improve your productivity with simulation. And last week we looked all about bolt connectors, and in the first lesson, one of these series, we looked at basically ways to apply contact. So what we'll be doing today is talking about 2 new techniques, and then, well, they're not new, they've been around for a couple of years, but a lot of people really still aren't familiar with them. But these 2 techniques are going to help you speed up your simulation and speed up your stress convergence techniques. So we're going to look at 2 different techniques today, guys, 2D simplification as well as submodeling. And what we'll do, I'm going to hopefully show you guys exactly what those features are, how to properly set them up, and give you some examples of when they can be used. So we're going to start with 2D simplification. So we'll start with an overview of plane strain, plane stress, and axi-symmetry. Those are the 3 main types of use for 2D simplification. Then we'll do an example of it. Then we'll jump into submodeling, and I'll explain what it is, why you can use it, and why you should use it, and then we'll go into an example of submodeling as well, and we'll have a Q&A section right at the end of that. So let's start with 2D simplification. And why do we talk about 2D simplification? SOLIDWORKS is a 3D program. We've spent a lot of time telling you guys why modeling in 3D is going to save you so much time, reduce errors, give you more accurate modeling, etc. Well, sometimes being able to simplify things down into 2 dimensions can have a lot of advantages, and almost all of those advantages are time-based. So what 2D simplification lets you do is look at just a 2-dimensional slice of your model. I'm not talking about a thin, like 5-degree wedge or anything like that, literally 2D. Now, what this is going to let you do is model things you either couldn't model before, or things that take a very long time to solve, and do it in a very, very short time. And 2D simplification is supported for linear studies, thermal studies, and nonlinear studies. So why, again, well, we'll talk about why in a second. When should it be used is what we'll talk about first. Well, there's 3 main cases where 2D simplification can be useful, and those would be plane stress cases, plane strain cases, and then axisymmetric cases. So what are those? Well, stress is where you have a very, very thin part subjected to mostly in-plane loads. So if you were looking at something like that part on the left, really the through thickness stresses may be negligible in there. As long as you don't have any loads going in that through thickness direction, all of your loads are sort of membrane type of loads, and we could very easily cut that down to 2D. Another example where this could be used is plane strain, and that's where you have something of constant cross-section that's essentially very long. And of course, the stresses may change at the end conditions of that pipe above, but through the vast majority of that pipe, the stresses are going to be constant. And that would be a plane strain simplification, taking a slice of that, ignoring the end conditions, and going for the middle sections of that pipe, what sort of stress do we see? And finally, axi-symmetry. Anywhere we have a revolved shape or anything that's symmetric about an axis, perfect case to break that down into a 2-dimensional study and save yourself a lot of time. So what's the benefit to start with? Why wouldn't we do it in 3D? Because we probably have a 3D model that we're going to analyze. Well, let's look at this case right here, just a simple linear static case of an O-ring seal. So we've got this double O-ring connection on basically a small little vessel here. And if you look at the cross-section, you can see a couple little O-rings that are embedded in with grooves. And this would basically be sealed. You'd have a pressure sort of forcing these together, and then you'd want to pressurize the vessel, see how your seals react. Well, we might look at 3 cases, a 360-degree revolve, just a 20-degree slice of that model, and then a 2-dimensional slice. Well, what do the solve times look like for that? Well, the 360-degree, the full revolve, that would take about 43 minutes to solve. If we cut down to a 20-degree slice of that model, we'd solve in about 11 minutes. And if we cut down to a 2D slice, 3 seconds. So that's where the time saving comes in. And of course, with all of these, you will expect to see very similar stresses between your full model, the slice, and the 2D slice. So massive time savings. And that's just for a linear study. What happens if we move to a nonlinear study? So in this case, we'll look at something where we're modeling the exact same thing, but we're using a hyperelastic material model, which is a nonlinear model for the O-rings themselves. Now, with something like this, we wouldn't even consider a full 3D model, it would just take far too long to solve. So we look at a 20-degree symmetric slice, a 2D slice with the same mesh settings as the 3D, and then a very, very refined model. All the no penetration contact around those O-rings has a lot of mesh refinement there, so we'll get accurate contact stresses and contact forces in that region. Well, we look at the solve time for these three cases, guys. Just the 20-degree slice would take almost 3 hours to solve. If we cut that down to a 2D slice, we'll solve in about 19 seconds, and even with a very, very refined mesh in the contact area, we're solving in less than a minute. So there you go. That's why we do 2D simplification. Do you want to wait 3 hours for results, or do you want to see those results in about a minute and move on and basically keep designing? So we're going to look at an example right now, and we'll look at a bellows type expansion joint for a steam pipe, and we'll look at a 2D simplification of this. This is a great axi-symmetric type of model. Now, we're actually going to do two different things here. First of all, I'll explain the loading in here. So we have hot, low-pressure steam running through this pipe, and there's kind of two loads that induces. One, there's thermal stresses in there. Due to that high temperature steam in there, we're going to get basically parts of this model that are much hotter than other parts, and that thermal expansion is going to induce some stresses. So first, we're going to run a thermal study to get the temperature distribution through here. Then we'll start a static study, and in the static study, we're going to basically use the thermal stress as well as pressurizing the pipe and also applying an end condition to compress the bellows a little bit. So I'll pop over into SOLIDWORKS, and we'll have a quick look at this right now. So here's the expansion joint we're going to look at today, and I'm just going to pop this into a symmetric configuration, guys, right here. So great example here. We have symmetry end to end. So why look at the whole model? We'll just start with the half model. Now, we'll use symmetry to make that behave like it were connected to the rest of the model. So how do I start a 2D study on this? Well, it starts the same as you would with a regular 3D study. I'm going to start a new study. And again, 2D is supported for static, thermal, and nonlinear. So I'm just going to show you a quick example with a static study here, and then we'll jump into a previously solved example. So when I'm choosing a static study, I'll just call this one 2D example, I just need to turn on this Use 2D Simplification option right at the very bottom of the screen and click OK. So what this does, this now brings up a second window here. We're still in the Property Manager, and I get to choose whether basically which three of those cases we're looking at: plane strain, plane stress, or in my case, axi-symmetry. So what does SOLIDWORKS need to break this down? Well, it needs the section plane as well as the axis. So in this case, it's symmetric. It really doesn't matter what plane I use. I'm going to use the front plane in this case, and for my axis, I'll select that line right there, that axis running right down the center. You can see it gives us a quick preview of what that section is going to look like. Then when we're done, we just click OK. And there we go. It's that simple. We now get to go in and start setting up this 2D study. And it's a little simpler than it would be setting up a 3D study. Because we're in 2 dimensions, there's less choices for restraint directions here. Now, that's how we set it up. I'm going to pop into some predefined studies here just to save some time. Now, I have a thermal study defined on this exact same 2D slice. And as I mentioned, we're going to try and find out what the temperature distribution is through this with hot steam running through it. So the first thing I have is a temperature load applied. And this temperature is applied to all the inside faces, the inside edges of this model where steam would actually contact the steel. And we've set that to 220 Celsius. Now, this is also being air cooled. This is outside. We have wind blowing over the outside of it, or at least natural convection from the air. So we've set some convection on all the outside edges that would actually see air. Now, with that, we can run the study, and very quickly, we'll see what the temperature distribution is. And I find my maximum temperature is 220 right on the inside surface there. That's what's showing in red. Most of the bellows here are at the same temperature. If I go in and probe this, I'll find out the inner edge. Well, that's going to be about, well, I actually won't probe it right this instance. Let me go back to an application probe. Well, my probe tool is not playing nice right now, but we see about a 2-degree temperature difference across the bellows, but we see a pretty significant temperature difference in the flange over here. At the upper point of the flange, the lowest temperature we see is actually about 190 Celsius. We've got over a 30-degree temperature difference there. Now, that's the temperature distribution. Next, we'll use that to do a thermal stress study on the part. So what I would do, I'd start a brand new study here, and the first thing I would do is include my thermal effects. And you can do this very quickly. If you go into your external loads, go down to thermal effects, right here, you can tell SOLIDWORKS to, well, 2 ways you can do this. You could either set it up by just specifying a temperature load, but we've actually gone in and solved that whole temp distribution. So in here, I can say, take my temperatures from a thermal study, and then I can select any thermal study that I've solved already. So this is set to bring in the temperatures from that study we just looked at as a load here, and it comes in just like that. Now, I mentioned there were a few other things we were doing here. In the stress study, we're also going to pressurize the pipe. So I have 0.3 MPa of pressure that's acting on all the inside faces of the model here. So you guys will see the pressure acting right there. And we also have some compression on the actual flange face itself. When the entire piping system heats up and expands, we expect this bellow to get pushed inwards a little bit from the pipe expanding. So what I've done is set up, whoops, I'm not going to suppress that. I have set up a condition here where we're basically pushing this edge, the sealing face of the flange, inwards by 4 millimeters. Now, remember, it is a symmetric model, guys, so if I'm pushing 4 mil on one end, we're basically assuming 8 mil compression on the whole model. The final thing I'd have to do here is actually set up my symmetry condition. And symmetry in 2D, very simple. All I need to do is select the symmetric edge. So I've gone in here and chosen that cut edge of the bellows and used that for my symmetry restraint. Now, when we solve this, we actually see something like this, guys, and I'm going to animate this right now. And you know what? I'll slow that down because it's probably a little bit choppy over the web connection. Let's go normal too. So you can see a couple of things happening here. The bellows is certainly compressing. We can see the stress developing around the upper and lower, or inner and outer surfaces of those bellows. But if I look over at the end condition here, we also see it expanding outwards a little bit. And that's, and when I say outwards, I mean radially in this case. And that radial expansion is due to 2 things. There's the pressure we put inside it, but there's also the thermal expansion. When we heat this up to 220 degrees, it gets a little bit bigger, guys. And again, this is about 6 times exaggerated, but you get the idea. So when I look at this, I can still get a very, very accurate stress distribution. I'll just show you the mesh on this right now. We've used a lot of elements here, and you can see through the bellows, we actually have about 4 or 5 elements minimum running through the thickness at every point in here. If we tried to run that mesh refinement on a full model, that level of mesh refinement, we would end up with just element overload, and I'll show you guys that in a second. But let's get back to what we can do with the stress results. So this 2D stress result is great. I can go in, I can see where my maximum stresses are, minimum stresses are, probe this, clip this, anything I need to, just like a normal 3D stress plot. And for engineers and designers, we're comfortable looking at this type of 2D plot, but if you need to show this to management or a customer, sometimes they go, well, what is this? This is just a slice. It's not the whole model. We have some great ways to make this look like it were the entire model. So just by right-clicking on my stress plot, you'll see this option to show as 3D plot. If I turn that on, by default, it's actually giving me a revolve, just a very small cutout section in here so I can see what's happening through the cross-section. And it does look like the entire model has been solved now. And it is just faking it. All it's doing is revolving that color plot around the axis. But these results are great for taking screenshots for reports, even animating this to get better visualization in 3D. So I can animate the 3D plot very quickly, just like that, and get some visualization on what the stress is doing in my entire model. So that is 2D simplification. And it's a very good tool, guys. In this case, we just looked at Axi-symmetry, but again, it's also good for plane strain and plane stress cases. Now, I'll show you guys a little bit more about why we couldn't do this in 3D, and again, it comes down to sort of element overload. I'm going to look at just a 3D slice of this model, guys, just a very, very small slice of it. There we go, this one right here. And if I use the same mesh settings on this that I did for the rest of, or for the 2D model, to get the same number of elements going through the thickness, let's see what that mesh looks like. Even takes a couple seconds to show here because there's so many elements, but you'll see it comes in very, very dense. There we go. And just looking at that very small slice in there, we have about 1 million elements. So about 970,000 elements in there. So this is a large model. Even a small slice would take a very long time to run. In comparison, if I pop back to my thermal stress study here, and we do a mesh element count on that, we're going to see we go from about 1 million elements down to something much, much, much smaller. If I go into my details here, well, here we're dealing with less than 12,000 elements, and that's where the solve time comes in, guys. From 1 million elements down to about 12,000 elements, the solve time is going to be that much faster. So that is 2D simplification. Now, in summary, I will say time isn't everything here, guys. If there are cases where you're wondering, is this really applicable for 2D, you may need to question that a little bit. Just because you can simplify it into 2D doesn't mean it's a proper thing to do. But as long as you're looking at plane strain, plane stress, or axi-symmetry, and you can ignore the end conditions, usually a pretty good thing to do. Again, useful results do matter in this case, so it is worth checking versus a 3D model, or basically trying to triangulate that if you can. But 2D simplification really offers some great benefits, an incredible level of mesh refinement, much faster solution times for the same mesh size, and like we just showed, we can solve problems that are virtually impossible to solve in 3D just due to mesh limitations. So that was 2D simplification. We're going to talk about another great simplification technique here called submodeling. And again, we're trying to reduce solve time in this case. So solve time really is the worst. It's just sitting around and watching your computer solve. And it's often tying up your machine so you can't be doing other useful work. Well, normally when you create a study and you mesh it the first time, you run it, that initial mesh isn't good enough to get a converged stress out of it. It'll give you a number, but we really don't know if that's a true number until we run some stress convergence. We'll do a finer and finer mesh until that stress stabilizes and basically steady states. That's when we know we're looking at a true stress result. Now, even though a coarse mesh we know will not give us good stress results, even a very coarse mesh will give us accurate displacements in the model. Displacement converges much, much, much faster than stress does. So as long as your mesh sort of accurately captures the geometry, you're not representing a circular face with a hexagon, something like that, you can get very accurate displacements out of that. And we're going to use this to our advantage with submodeling. So this would be where I do the second poll question and say, how many of you guys need to look at a single part of an assembly in greater detail, or even a single area of a part in greater detail? Now, normally, if we were to do this on this little scaffold here, I'll talk about this more in a second, this could take a while to solve. And what I have, I've got my scaffolding frame here, but we have this platform on top, and it actually connects with these little hanger joints. It literally just sits on top of those crossbars, and it can slide around back and forth. So there's no penetration contact there. If I'm trying to resolve the contact stresses in that region where the hanger kind of sits on those bars, if I'm trying to solve that in the whole model with all that no penetration contact, all those elements, it's going to take a very long time to solve. So we're going to look at how submodeling can help us just zero in on those few components. So submodeling lets us conveniently isolate a very, very specific area of the model. That could be one part or one component or multiple components, and analyze it in greater detail without solving the whole model. Now, how does it work? Well, as I said, we're going to take advantage of knowing that even a coarse mesh gives us good displacements. So the first step is to create a parent study with a very coarse mesh on it. And we're not trying to get refined mesh or converged stress, we're just looking for displacements here. And because we have a very coarse mesh, this is going to solve quite fast. Then, once that parent study is solved, we'll create a submodeling study from it. And we'll tell SOLIDWORKS which components we'd like to look at. And then we'll use basically a much finer and finer mesh on those components to get that stress convergence. Now, how does that work? When we're looking at just a few components, how does it behave like it were attached to the whole model? Well, the displacement from your parent study is actually transferred to the edges of your submodel as a boundary condition. And what that does, it actually forces your submodel into the exact same deformation it would see in the parent study. So with that, the displacement being transferred, your submodel basically behaves like it were connected to the rest of the study. Now, once basically we have that set up, we can run that submodel over and over again, trying smaller mesh refinements, small geometry refinements, etc., and solve it in much less time than solving the entire model. So let's look at this in a real example right now, and we'll look at this scaffolding platform. So as I mentioned, we have this sort of platform stand here with some bracing on the bottom, and then we have the platform on top of it, where we've got some beam elements, a piece of wood on top of it, and it's being loaded with some weight. Now, we'll start by running that as a master model, very, very coarse mesh, or sorry, a parent model. Then we'll do a submodel just on one of the hangers, and with that, we're going to isolate some of the components. And one useful thing you'll see here, guys, these beams that have sort of been split here in the corners, the ones that are highlighted in blue, those have been created basically by splitting a beam into two beams. You can do that just by creating two end-to-end sketch lines with beam elements, or using the split command to split bodies that way. So it can be useful to sort of split your bodies if you want to look at small areas of those bodies. Now, I'm going to pop into SOLIDWORKS and show this to you guys live. So here is my scaffolding right here, guys, and I'll show you the parent study that I have set up. Let me just pop over to that. Now, with this, we've gone in and defined everything that needs to be defined. I'm not going to walk you guys through the basic study setup. We defined the joint group. We have some forces acting downwards on the beam. We also have gravity turned on, and we also have a side load turned on as well. Now, with this, it's a very, very coarse mesh, and I'll show you guys what the mesh actually looks like. So I'm going to look at one of the hangers in detail here. That's not a refined enough mesh to give us even a close to accurate stress in here. What we do, in this case, we only have one element going through the thickness. We would need a minimum of sort of 4 or 5 in there. I'd like to have a lot of element density right around the contact area, so I can see basically good resolution of how deep those contact stresses go. Now, if I pull up a stress result on this, this is essentially what we look like. And well, I don't want to look at the beam stresses. I want to look at the solid and shell stresses. So as I zoom in, again, definitely not enough refinement. Anytime you see that jaggedness in your stress plots, you're seeing basically really, really, really low mesh density. So if I pop over to a strain plot, right now you'd see, yeah, that is not going to give us an accurate representation of anything in the model. So how do we create a submodel out of this? Well, very easy to do, guys. Once you've solved your parent model, right-click on the parent study and use this option, Create Submodeling Study. So it gives us some interesting information here. It tells us what it does, but it does give us some limitations as well. Your parent study must have more than one body, because there's no advantage in using submodeling on a single body. All bodies are treated as solids by default unless you change them. And then you can't have purely no penetration contact in your parent study. There has to be some sort of bonded contact in there. And finally, you can't basically be connected from your submodel to your parent study with connectors. So if it's bolts holding your component onto your parent study, or pins, springs, etc., that's not going to work. It has to be basically bonded to your parent study. So when I do that, let me just do this one more time, guys. As soon as I click OK there, it gives me this list. And these are all the bodies I could include if I want to. And all I would do is go in here and tell SOLIDWORKS which bodies I want to include. Just by selecting them like that, we see it selects them in the tree for me when I pick them graphically. When I click OK right now, it's going to define a submodeling study. And I'm not going to click OK right now because it actually takes about a minute or two to go through and create the submodel and then transfer the boundary conditions over. So I'm going to look at a predefined one. Let's pop over to this submodel. And I selected the exact same components here, guys. I'm just going to activate the configuration. You can see even activating that configuration takes quite a while. It's going in and suppressing certain components, transferring those boundary conditions, etc. But again, much, much faster to use these submodeling studies than to run the whole model over and over again. So as soon as this finishes its suppression, it's going to show us the submodel. And there we go. This is our submodeling study. So it's automatically gone in and suppressed everything else. You can see that in the excluded bodies folder, but there's something really neat in here. If I look under my fixtures, I see this displacement from parent in here, and I can see it's applied to all of the edges or cut faces where my submodel connects back to the parent model. And this is how the submodel behaves like it were connected to everything else. We're physically twisting and pushing on those ends to push it into the exact same shape that the parent model deformed into. Now, what we can do here, you'll see the loads have automatically transferred as well, any applicable load, so just the component of force that's acting on this part of the study, and the gravity load that was there as well. And then I can go in and run this. Now, with a submodeling study, the main advantage here is we can do much, much finer mesh refinements. And I've gone in, you'll see the mesh level I have in here. I've used a very small growth ratio and a very small mesh right at the contact area, so we have lots of elements in that contact region. Now I can run this, and it only takes about a minute to run this, guys, compared to about 10 minutes to run the parent study again. And that parent study, that was about 5 to 10 minutes to solve, even with a coarse mesh. So let's see what we have for stresses in here. Now, even though the stress looked just like garbage in our parent study, with a fine mesh refinement in here, I can see exactly where my high stress regions are and how deep those stresses are as well. In this case, we're not actually yielding at the moment. The yield of this material is about 205 MPa, 206 MPa. We're only at about 153 right now, but even if we did see some localized yielding, we'd have a refined enough mesh in here to see how far does that yield actually go through the part. Are we just going to end up sort of curling back the edges in here and maybe flattening out or hammering out that outside edge, or are we going to see a yield failure on the entire bracket? Well, in this case, we're safe. We can see exactly where the highest stress regions are, and I can also see that that very quickly bleeds back to a very, very low stress. If I look at the center of that bracket, we're dealing with stresses in the 150 range in here, guys. So, I'm sorry, much lower, not 150. We're seeing 62 MPa, we're seeing 12 MPa, we're seeing 19 MPa. So very, very low stresses in the majority of the brackets. And that submodeling, I could go in now, if I still wasn't convinced this was a converged stress, I could create another submodeling study or try out subsequent smaller and smaller mesh refinements until I see a converged stress. So that's submodeling. It's a great tool to use, guys. And in summary, it is a really, really good time saver. The technique is run the parent study, very coarse mesh just to get your displacements, and then force your submodel to deform with those displacements and try out smaller and smaller mesh refinements. I alluded earlier that you could actually even use this for small geometry changes. If I wanted to try out some different size fillets on here or different radiuses of curvature, I could do that in a submodel. It will let you tweak the geometry, but I want unsuppressed and unsuppressed features as well. But you have to be careful. If you're doing something that's going to change the overall stiffness of the model, you have to go back and rerun the parent study first, and that will resolve the displacement field. Then you can go in and use the submodeling for stress convergence. So those were the two techniques we reviewed today, guys. We talked about 2D simplification great for plane strain, plane stress, and axi-symmetry. And we also talked about submodeling, which is really good for zeroing in on sort of one or two components, running some mesh refinement, and doing it in much, much less time than you normally would. So that's all we have for today, guys. I hope you found this useful, and I hope you're going to use these in your own studies, or at least try them out and see how much benefit you get out of it. Once again, I'm the Simulation Product Manager at Javelin. My name is Peter Chelboten, and my contact information is up on the top of the screen there. Feel free to give me a call or extension 270 from any of our numbers across Canada, or send me an email. I'd be happy to connect with you one-on-one, talk about this in more detail, or answer any other simulation questions you have.